In this video, we're going to talk about the unit tangent, normal, and binormal vectors. So something called the TNB frame. Okay, so let's begin with a definition. If a curve C is represented by a smooth vector-valued function r of t, then we define capital T of t to be r prime of t divided by the length of r prime of t. So we call t of t the unit tangent vector to the curve at C. So notice that r prime of t will be a tangent vector to the curve. Okay, so we've talked about that. R of t is some curve in 2 space or 3 space. R prime of t will be a tangent vector, but if we want the unit tangent vector, we'd have to take that tangent vector and divide it by its length. Okay, so t of t will be a tangent vector of length 1. It'll be the unit tangent vector. Okay, so notice that for a given value of t, t of t is tangent to the graph of t. It has length 1 and it points in the direction of increasing parameter. Okay, so let's look at an example. Find the unit tangent vector to the graph of r of t equals t squared I plus t cubed j at the point where t equals 2. Okay, note, even though the graph is not a smooth function, this is not a smooth vector-valued function, we talked about that in the previous video, it is smooth near t equals 2. Okay, so I've drawn the graph of this here in Desmos, right? We have t squared comma t cubed, and it's being traced out in this direction. Notice we do have the sharp corner there, but when t is 2, where are we at? Well, when t is 2, we're at the point 4 comma 8. Okay, so we're at this point 4 comma 8, which is right here, right? We're at 4 comma 8. The question is, what is the unit tangent vector they're going to look like? Well, the tangent vector should be facing off in this direction here, right? Have a length of 1 facing this direction, right? Since it's being traced out this way, it'll be a unit vector in this direction. Okay, so how do we find that tangent vector? Okay, well, let's come back here. So first of all, we take the derivative, right? So r prime of t is 2t comma 3t squared. The norm of r prime of t is going to be this, right? The square root of 2t quantity squared plus 3t squared quantity squared. And we end up getting the square root of 4t squared plus 9t to the 4th. Now you could factor out a t squared if you wanted to and write it as a square root of a t squared times the square root of something. But let's just leave it like this. Okay, so remember our capital T of t, right? Our unit tangent vector is going to be r prime of t divided by the norm of r prime of t. So I've written here 1 over the norm of r prime of t, that's what this is, times r prime of t, and that's what this is. Okay, and so notice what we do. We have a scalar multiplication here. We have a scalar times a vector. So we multiply each of the components here by this. Okay, and this is what we end up getting. So that's t of t. That's the formula for t of t, for any value of t. Now when t is 2, we can plug in 2 for each of these t's, and what we'll get is 4 over the square root of, well, it would end up being 4 times 4, which is 16, plus 9 times 16, which is 144, and 16 plus 144 is 160. Okay, and if you plug in 2 for there, you get 12 over 160. So the point is, this is the unit tangent vector. Now we can simplify this a little bit. The square root of 160 is like the square root of 16 times the square root of 10, and the square root of 16 is just 4. So this is really 1 over the square root of 10. Okay, right here. And you can do the same thing here with the denominator, but 12 over the square root of 16, or 12 over 4 would be 3. Right, so we get 1 over the square root of 10, comma 3 over the square root of 10. If you write it out as decimals, this is what it is. Again, you can check for yourself. This has a length of 1, right? If you do the square root of this squared plus this squared, you're going to get the square root of 1/10 plus 9/10. And that's the square root of 10/10, right? The square root of 1, which is 1. So notice this is a unit vector, and it turns out it's the unit vector that's the tangent vector, the unit tangent vector to this curve. Okay, now recall from a theorem at the end of section 12.2, see the notes here, that if a vector-valued function r of t has a constant norm, okay, so like if you're in 3 space, the r of t always lies along on some sphere, maybe a sphere of radius 5, so it's the constant of 5. Then r of t and r prime of t will be orthogonal. Now it's very important. R of t and r prime of t are not usually going to be orthogonal to each other, but in this particular case, they will be. It'll be the case that if the r of t has a constant norm. Okay, so notice in particular that t of t has a constant norm of 1. Okay, so t of t would be one of these functions that does have a constant norm. So t of t and t prime of t should be orthogonal. Okay, so that means that t prime of t will be perpendicular to the tangent line to the curve at t. So we're going to define n of t, this will be called the unit normal vector, to be t prime of t, right, which is orthogonal to t of t, divided by the length of t prime of t. So if you take a vector and divide it by its length, you get a vector of length 1. So n of t will be called the unit normal vector, right? So it has a length of 1 because you're taking a vector and divided by its length. So n of t will have a length 1. And it will be orthogonal to t of t. Okay, so notice that the unit vector n of t is only defined at points where the t prime of t is not the 0 vector. If we have the 0 vector down here, it will be undefined. So we'll assume that that condition is satisfied in most of our examples we're looking at. However, that will exclude straight lines. Right, so let's look at an example though. So suppose we have some curve, some vector valued function. Now I've drawn it in 2 space because it's easier to draw it that way. But that's being traced out here. So this is some r of t, gives you this curve here. Then at some particular point t, okay, you could call it t naught, or maybe it's at 2 or something. Maybe t is 2. So maybe t of 2 would be this unit tangent vector. N of 2 would be orthogonal to that. So notice n of 2 kind of points inside. If the curve is bending like this, it sort of points inside the place where it's bending. T is the tangent vector, and n here is the unit normal vector, right? If we go along here, notice that over here, the t would be this way, the n would be pointing inside. So in other words, as the curve is bending this way, the n of 2 would point inside. Now, there are certain places where it kind of changes from bending one way to bending another way, so kind of like an inflection point type thing, where the n of t won't exist. So there'll be some point in here, probably another point in here, another point in here, where the n of t won't actually exist because, you know, you'd wonder, would it be pointing this way or this way, and it actually wouldn't exist because the t prime of t would actually be 0 at those points. Okay, so we have this unit tangent vector and the unit normal vector. Okay, and you can also do this in 3 space, by the way. In fact, if C is the graph of a vector valued function in 3 space, we could define the unit binormal vector of C at t to be this. So the binormal vector is just the cross product, t of t cross n of t. So B of t has a length of 1. Now, why does B of t have a length of 1? Well, remember that the length of the cross product will be the area of the parallelogram determined by these 2 vectors. But these 2 vectors both have a length of 1, and the parallelogram determined by those 2 vectors is really just a square, right? It's a 1 by 1 square. So the length, or the area of that square, right, it would just be 1 times 1, which is 1. So that's the norm of B of t. So B of t would have a length of 1, no matter what the t is, and that all these are orthogonal to each other, because remember, B of t will be orthogonal to both of these 2 vectors. And t of t and n of t were already orthogonal to each other. Okay, in fact, the coordinate system that's kind of determined by these, the t of t, n of t, and b of t, is what's called the TNB frame. So let me show you a little video here that has an animation of this. Okay, and this is really just here in Wikipedia. If you find, like, if you Google, well, this is under this definition, Frenet-Serre formulas, but I just Googled TNB frame, and it came up with this. So notice here, what we have here is some curve that's being traced out here. Okay, and you see the curve moving along. This blue one, it's hard to tell the colors here, but this blue one looks like it's the t of t, right? It's the unit tangent vector. It's pointing in the direction that the curve is going. The red one, the one that's pointing to the inside, that's like your n of t. That's your normal vector, right? That's pointing inside. And then this black one that's pointing up, that's orthogonal to both of those 2, that would be the unit binormal vector. So we get the unit tangent vector, the t of t, the unit normal vector, the red one would be the n of t, and the binormal vector would be the black one, that's the b of t. Okay, let's look at, I think there's a couple more good examples here in this article. This article probably gives you a little more information than you necessarily need, but if you want to find more about this, you can look here. Now notice they've drawn these a little different colors. It looks like the blue one in this case is the t of t, right? And it looks like the green one is the one that's pointed inside. Actually, probably a better one would be this one right here. Okay, see, watch the curve being traced out. Notice which one is the tangent vector. Well, it looks like the yellow one here. It's pointing in the direction that the curve is going. Okay, now which one is the green one? Well, the green one looks like it's the normal vector. It's pointing sort of inside the curve. Okay, and then the blue one would be the binormal one. That's orthogonal to the tangent one and the normal one. Okay, by the way, each of these 3 vectors gives you a plane, right? So this curve is in 3-dimensional space here. It lies in 3-dimensional space. It almost looks like the curve is within this plane, but this portion of the curve is behind the plane, then it cuts through the plane right here, and then it looks like this. So you get some curve in 3 space. Well, the plane that's determined by n and t is called the osculating plane. And by the way, as your point moves along the curve, this frame itself will move along the curve as well, as we saw in that last animation. And so this this plane itself will kind of move along and wobble along the curve as it's being traced out. So that nt here, that plane that's determined by those is called the osculating plane. Now, I have this in fact, let me go back to the notes here. The three vectors determine three planes. The TB plane, called the rectifying plane. The TN plane, called the osculating plane. That's the one we just looked at. And the NB plane, called the normal plane. So if we go back to our Wikipedia article here, so with the NB plane, so if you drew the plane that contains these two vectors, N and B, okay, the plane that goes through those, that would be called the normal plane. Okay, and if we looked at the plane that contains these two vectors, B and T, that would be called the rectifying plane. Okay, but the plane that's drawn here is the osculating plane. And as the point moves along the curve, all three of those planes are kind of moving as well. Okay, so that's called a T and B frame. Okay, now it turns out that B of t can actually be calculated directly from R of t as follows. And you don't need to memorize this, or at least I don't expect you to memorize it. It's R prime of t cross R double prime of t divided by the norm of that. So remember, how would we normally calculate B of t? Well, the way that you normally calculate B of t would be you would calculate T of t. And the way to calculate T of t is to do R prime of t divided by the norm of R prime of t. And that can be kind of messy. Okay, notice that this is what T of t is. That's kind of messy. Okay, and if we wanted to calculate N of t, then we have to calculate T prime of t divided by the length of T prime of t. And that can be very messy, because what's T prime of t? Well, we have to take the derivatives of each of these, and that could be messy. In fact, when we do the norm of those derivatives, so you're doing the square root of that thing squared plus that thing squared, it could be even more messy. Right? So you can get a very messy formula for N of t. And then the B of t, you'd have to take the cross product of those things, so it can be even more messy. And so sometimes it's nice to have a formula where we can calculate B of t directly from the R of t. Okay, now there are some very nice simplifications for curves that are parametrized by arc length. Okay, this is very nice. So suppose R of s, and notice I've written R of s instead of R of t, because we're assuming it's parametrized by arc length. Okay, so see the last video here for what we mean by parameterization by arc length. So suppose R of s is parametrized by arc length then by a theorem in section 12.2, the norm is always constant, right? The norm is 1. And so notice that T of s would be R prime of s divided by the norm of R prime of s, but the norm of R prime of s is 1. So T of s would just be R prime of s. Right? So R prime of s, right, would just have a length of 1, right, if it's parametrized by arc length. Okay, and then also N of s would be R double prime of s divided by the norm of that. But just to point out here, these formulas only work for curves that are parametrized by arc length. Okay, so that's why I'm using the letter S here. Okay, so don't use these formulas unless you know your curve is parametrized by arc length. Okay, so let's finish with an example where we actually calculate the TNB frame at a certain point here. So let's let R of t be this. So ti plus the square root of 2 over 2 t squared j plus 1/3 t cubed k. So you could also write it in the bracket notation like this. Now find t of 1, okay, the unit tangent vector when t is 1, n of 1, okay, the unit normal vector when n is 1, and b of 1. Okay, now this could be a bit messy, but actually you might think I just kind of randomly wrote these things down. I actually put down some formulas here for the coefficients of the I, J, and K that actually makes this easier. Okay, makes it less messy. So I kind of rigged this up to not be as messy as it could have been. But okay, so R of t is this, right? We have this R of t. R prime of t, what's the derivative? Well, the derivative of t is 1. The derivative of the square root of 2 over 2 t squared, well, we bring the 2 out front and lower this power to 1. The 2's would then cancel, and we end up with just the square root of 2 times t. Okay, now the derivative of 1/3 t cubed would be t squared. Okay, so this is R prime of t. Now we have to calculate the norm of R prime of t, because remember, we're trying to figure out t of t. Now ultimately we want to figure out t of 1, but let's figure out t of t first, and then we'll plug in t equals 1, little t equals 1. So t of t is R prime of t divided by the norm of R prime of t. So then we have R prime of t already. The norm of R prime of t would be the square root of this squared plus this squared plus this squared. And if you do this, you get the square root of 1 plus 2t squared. If you square this, the square root of 2 squared is just 2, and t squared is just t squared, and then plus t to the 4th. Now, I rigged this up to be nice, because actually 1 plus 2t squared plus t to the 4th is actually t squared plus 1 times itself. If you FOIL this out, t squared plus 1 times t squared plus 1, well, t squared times t squared is t to the 4th. You get a t squared and another t squared gives you 2t squared, and then 1 times 1 is 1. So in other words, it's the square root of t squared plus 1 squared, and the squared and the squared go away. So again, I kind of rigged this up to be nice, but we get the norm of r prime of t is just t squared plus 1. So t of t is r prime of t divided by the norm of r prime of t. Okay, so the norm of r prime of t, remember, was t squared plus 1. So we have 1 over t squared plus 1 times the r of t, which is right here. Okay, so we can do this scalar multiplication now. Multiply this scalar by this vector. So we multiply each of the components by that vector, and this is what we get. So there's our t of t. Now what's t of 1? Well, if we plug in 1 for t everywhere here, we get 1 over 1 squared plus 1. That's 1/2. If we plug in 1 here, we end up getting the square root of 2 over 2. And if we plug in 1 here, we get 1/2. Now notice, by the way, this vector has a length of 1. If you were to do the square root of this squared plus this squared plus this squared, you would get 1. Because it would end up being the square root of 1/4 plus 1/2 plus 1/4. Okay, so that would end up being the square root of 1, which is 1. So this is a unit vector, and not only that, it's tangent to the original curve at t equals 1. And I've not even attempted to try to draw this original curve, r of t. Okay, but if we did, that when t is 1, this would be the unit tangent vector. Okay, now how do we find n of t? Now remember, n of t is going to be t of t, or I'm sorry, t prime of t divided by the norm of t prime of t. Okay, so let's figure this out. What is t prime of t? Okay, t prime of t is, well, here's t of t was this. To do t prime of t, we're going to have to take the derivatives of these. And that's going to be a little messy, but we can do them using the quotient rule. So here's what you end up getting, right? So if you do low d high, so that'd be the bottom times the derivative of the top. Now the derivative of 1 is 0. Minus high d low, so that'd end up giving you a minus 2t there. All over the low squared, you get this. Okay, if you do the low d high minus high d low of this, you end up getting this, and same thing here, you get this. Now you can simplify these, so it's a little bit messy, not terribly messy, but if you simplify it, you end up getting this t prime of t. Now if we wanted to find the norm of t prime of t, it'd be the square root of this squared plus this squared plus this squared, which would be messy. But actually, we don't even need to do that though. We're really just trying to find n of 1. So n of 1 will be t prime of 1 divided by the norm of t prime of 1. Right? N of t would be t prime of t divided by the norm of t prime of t, but we just need to find n of 1. So we really can just plug in 1 for t here. So if we do plug in 1 to find t prime of 1, if we plug 1 in everywhere we see a t here, we end up getting negative 2/4, comma 0/4, comma 2/4, which is negative 1/2, 0, 1/2. Okay, so that's t prime of 1. Now we have to take that and divide it by its length, because this does not have a length of 1. Right? If you do the square root of this squared plus this squared plus this squared, you're not going to get 1. So we have to take t prime of 1 divided by the length of t prime of 1. That will be our n of 1. Okay, now t prime of 1, again, was this. The length of this, though, is just the square root of 1/2 squared plus 0 squared plus 1/2 squared. And you end up getting this divided by the square root of 1/2, which, by the way, if you're dividing by the square root of 1/2, it's the same thing as multiplying by the square root of 2 over 1, or just the square root of 2. Okay, and so if you do that, you end up getting this. So this is your n of 1, and you can check this is a unit vector. Okay, it has a length of 1 if you do the square root of this squared plus this squared plus this squared. So it's a unit normal vector. It has a length of 1, and it's orthogonal to t of 1. Right? We found our t of 1 right there. Here's our n of 1. How could you check that t of 1 is orthogonal to n of 1? We'll take their dot product. Do this thing dot with this, and see, do you get 0? And you can check it for yourself. Okay, if you do 1/2 square root of 2 over 2, comma 1/2, dot with this vector, you'll get 0. Okay, now finally, what about b of 1? Well, it'd be messy to try to find b of t. And in fact, we didn't even find n of t. We only found n of 1. So it'd be messy to try to find b of t for a generic value of t. But we're just trying to find b of 1. So b of 1 will be t of 1 cross n of 1. Well, t of 1 was this vector, 1/2 square root of 2 over 2, 1/2. And n of 1 was this one we just found, negative the square root of 2 over 2, comma 0, comma the square root of 2 over 2. So if we work this out, if we find this cross product, so we're going to have this times this minus this times this, I. Now the square root of 2 over 2, comma the square root of 2 over 2 is going to be 2/4. Okay, minus 0 times 1/2, so it'd be 2/4 minus 1/2. So minus 0. So that ends up just being 1/2. And then you can do the minus, the determinant with the j, and then the plus, the determinant with the k. It turns out this is what you get. 1/2 negative square root of 2 over 2, comma 1/2. And this is the unit binormal vector. This is b of 1. And again, you can check. b of 1 is orthogonal to n of 1 and t of 1. Right? Take the dot product of these two vectors. See what you get. Okay? In fact, let's just do this in our head. What's this dot this? Well, we'd have negative square root of 2 over 2 comma 1/2. That would be negative the square root of 2 over 4 plus 0 times this. That'd be 0. And then plus this times this. So that'd be positive the square root of 2 over 4. So you'd have negative the square root of 2 all over 4 plus 0 plus positive the square root of 2 all over 4. And so that ends up giving you 0. So the b1 is orthogonal to n1, which is what we just had up here. But it's also orthogonal to t1. Right? So n1, t1, and b1, they're all orthogonal to each other, and they all have length 1. So check to see this as length of 1. Okay, so t is tangent to the curve, n sort of points inside the curve, and b is orthogonal to both of those. Okay, so this is the TNB frame.